for those of you at home, because it's going to go a little bit in and out of the way as I move over here to start recording. Oh, it's not following me, so maybe it's going to be OK. All right, so I will just play some of the opening scene.
Ina said as long as I was escaping, when I mind escaping to the market and picking up something for dinner. Sure, that was all I needed. A busy supermarket. I needed to drive, mellow out, get my mind off the wedding. But mellowing out was not in the cards. Yeah.
Excuse me, sir, what are you doing?
I'll tell you what I'm doing. I want to buy 8 hot dogs and 8 hot dog buns to go with them. But no one sells 8 hot dog buns. They only sell 12 hot dog buns. So I end up paying for 4 buns I don't need. So I am removing the superfluous buns.
I'm sorry, sir, but you're going to have to pay for all 12 buns. They're not marked individually.
Yeah. You want to know why? Because some big shot over at the Wiener Company got together with some big shot over at the Bun Company and decided to rip off the American public. Because they think the American public is a bunch of trusting nitwits who'll pay for things they don't need rather than make it stink. Well, they're not ripping off this nitwit anymore because I'm not paying for one more thing I don't need. George Banks is saying no.
Who's George Banks?
Me!
Why don't we just calm down now, sir?
I'll tell you why we don't calm down. Because you're not excited. It takes 2 people for a we to calm down, doesn't it?
That I don't know, sir. I'm just the assistant manager of a supermarket.
So I will just end what happens to people who try to do linear programming the way you're not supposed to do it. And so can you turn on the lights? So this is sadly a real danger. Now, of course, did anybody keep track of how many hot dog buns he was buying? So, and if he's buying 24, what could he have done? Yes, exactly, exactly. So, one of the subtle points of the movie that's often missed by people. So again, this is to just really drive home the point of what are the constraints. You know, can you buy things continuously, or are you forced to buy things in discrete amounts? If you can buy things in discrete amounts, you often have severe restrictions. And in fact, we do not have nearly as good of a theory for discrete cases as we do for continuous. For some things, you can assume a continuous distribution. And if you're looking at shares of Microsoft, shares of Google, the company is so big, there's so many shares, you might as well just assume it's continuous. Same thing for amounts of oil being shipped. Okay? We don't have to worry about, on the Planck scale, there's at some level an amount of oil you cannot go below. All right, so what I want to do now is I want to talk a little bit about how we would try to solve linear programming problems. We've done a little bit about how you would formulate them. But more than just solve them, solving is hard. If you can't solve something, what could you do instead? Approximate. And if you're going to approximate a solution, what would you like to know about your approximation? Your error, that it's close. So one of the great miracles of today's lecture, if we get there, is I'm going to show you a way to bound how far you are from the true answer without knowing the true answer. Okay? If you stop and think about it, this is miraculous. I don't know what the answer is, but I know my error is at most this much. There are a lot of things where we can actually bound errors like this. If you look at some series expansions, we might know some ideas. We might be able to estimate the tail and get a sense of how close we are. And so for a lot of things, we can get so close to the solution that it's OK that we haven't hit the optimal solution. Another thing is, in the real world, we often don't know the parameters for our model. So if you don't know the actual parameters, to insist on solving a model perfectly when the model itself is only an imperfect approximation of reality is a bit much to assume. I'm actually working to get the Berkshire Transportation Company to come and give a lecture to us on, hopefully this Wednesday, about the issues they're facing and give us some real jobs to do for the region. So I will let you know how that goes. So what I want to do today is I want to talk about duality. Okay, and so what I want to start off with is the chess problem. So the way I want you to think about this is, due to budgetary cutbacks, we can only afford a 5x5 chessboard. I have used too much money on buying superstar destroyers. In fact, I just bought 2 more superstar destroyers for winter study. And if anybody is interested in Lego challenges like this, let me know. If people want to have an operations research class Lego challenge, let me know. And I'm happy to buy 2 sets, 1 set to practice on, 1 set for the actual timing. It will not be the superstar destroyer because I do not have that much money available for something like this. All right, we have a 5x5 chessboard. We have 5 queens, and we have 3 pawns. And if I put a queen down on the board here, a queen can kill anything in that row, anything in that column, or anything diagonally. And the question is, how can I put down 5 queens in such a way that 3 pawns are safe? Okay? I do not want the best way to do this problem. If you know the best way, please keep it to yourself right now. Can someone give me a way to try to attack this problem? Be a pure mathematician. I do not care if it is efficient. I want a bad way to solve this problem. Yes?
Every possible combination or every possible permutation of putting this equals number.
Okay. So one thing is to just, good, that's even worse than what I was thinking of. Wow. Excellent. Remember to email me. So, wow, okay. So we have 25, well, technically it's 25, choose 5. We choose, because it matters where the queens are placed and where the pawns are placed. So it's 25, choose 5. I choose 5 places to put down the queens. And then of the remaining, how many squares do I have left? And I have to choose 3 of the squares for the pawns. This is an excellent theoretical answer, and it's an excellent, horrible, horrible practical way to do it. What part of your approach can I eliminate? Yes?
The placing of the pawns.
Yeah, there's no need to place the pawns. I mean, why would you do that? That's just silly. Right? There's no need to place the pawns. Once I place the queens, I can just calculate, are the pawns safe or not? How many squares are not attacked by the queens, and just count. Is there at least 3 squares that are safe? So I can at least drop the 20, choose 3. That's a great savings. We can do a little bit better than this. Have I talked to you about my tic-tac-toe prowess yet? It's been a while, but for a while when my kids were younger, we would go to the elementary school playground, which is not that far from my house, and a lot of the kids would challenge me to games of tic-tac-toe. And as you will find out if you haven't had a class with me before, I don't believe in going easy on people. I believe in introducing people to life is hard. And on the playground, I was good. Not one kid has ever beat me in tic-tac-toe. One kid did tie me once. Okay? I'm sorry? Not like sheep.
Well, isn't there just the best move, though?
Well, here's the thing. Let's play tic-tac-toe right now. And if you want, there are actually versions of tic-tac-toe that are fun. This is not one of them. But if there's time today, I'll actually discuss fun versions of tic-tac-toe. It's a great area of modern research. How many opening moves do you have in tic-tac-toe? I had 9 opening moves. 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have 9 opening moves. How many responses are there? How many responses to responses? Responses to responses to responses. Responses to responses. And? Not necessarily. At this point, someone might have won. We could have the game, right? And with some of these elements, now, they weren't quite that bad. I mean, my victories were more impressive than this. And I did go second. Okay? So if you have a situation like this, will you ever have a next move? No. So it starts becoming a little painful to analyze a problem like this in full detail. You can approximate, you can get an upper bound, and an upper bound is this 9 factorial games. Fortunately, I have a phenomenal memory. I can't remember your names, or I can't remember, are you in linear programming, are you in operations research, I can't remember small things like that, but all the different possible tic-tac-toe games I can remember. And there's only 9 factorial things to remember. Yes? Okay, so I can exploit symmetry. So really, how many opening moves are there? There's really only 3 opening moves. You can move in a corner, you can move in a middle, or you can move in the center. So there's really only 3 opening moves. Okay? And what do you think the elementary school kids mostly do? Usually they go for, sometimes they will go for one of the corners, but usually they'll go for the center. Two is, that's an interesting question as to what is the best. You have to decide what is your metric. If you were playing against somebody with a modest level of intelligence, it doesn't matter. Every game will end in a tie. So in some sense, it doesn't really matter. But what if you now put in a finite probability of a brain freeze, or somebody's giving a boring colloquium and you fall asleep? And we can actually test this later today. Okay? And so if I start to fall asleep, just whoever's sitting next to me, hand me a tic-tac-toe game with some moves, and I have to respond immediately. Okay? So somebody sit next to me today, we'll try that. All right? So when you say which move is best, I think you would have to say, assuming some probability of a mistake by the next player, which one is more likely to win? Which square do you think is the most valuable? The center. It's involved in 1, 2, 3, 4, 3 in a rows. Whereas this one is only involved in 2, this one is involved in 3. So it gives you, some relative sense of which ones you care about the most. So there's 3 initial moves. If somebody goes in the corner, how many responses are there? So how many responses? 5. 1, 2, 3, 4, 5. So by symmetry, there's really only 5 responses if somebody goes in a corner. What if somebody goes on a side? How many responses? Well, it's 1, 2, 3, 4, 5 responses there. And if they go in the middle, how many responses? 2. So before, we had 9 times 8. We had 72 possibilities for the first 2 moves. Now what do we have? If we go in the middle, there were 5. I'm sorry, if we go in the corner, there were 5 responses. If we go on the side, there's 5 responses. If we go in the middle, there's 2 responses. So we go from 72 to 12. A factor of 6 savings in terms of what you need to do. So this is a great principle. So instead of having to keep track of all those different games, it's much, much easier for me. Okay? Let's apply that over here. So we were told there's 25 choose 5 ways of choosing where to put the queens. Is there really 25 choose 5? Or can we do better? How many opening moves are there for the queen? So, yes. 6. 1, 2, 3, 4, 5, 6. The rest is going to follow from symmetry. So if you then look at what happens next, if you're just really crude and say I'm going to put down a queen, and now I have 24 squares and I have to do 24 choose 4. So it's 25 choose 5 versus 6 times 24 choose 4. And you can compare the 2 of these and see how much better is this than that. Okay? Now, of course, it's a bit wasteful if you just say the 6 over here and then just start choosing the next one completely at random. What are you losing when you do this? When you go to the 24 choose 4, what are you losing? You're losing symmetry. Why would you ever want to lose symmetry? Symmetry is great. You're giving yourself more cases to consider. Why would you want to consider more cases? I mean, you're giving yourself more work to do. Why would you do more work? Can anyone think of any reason why we would want to do more work than less work? And I'm not being paid by the computation. You know, I'm not Charles Dickens. Right? Why would you want to do more computations? This is one of the, yes?
Maybe you're interested in suboptimal solutions as well.
No. I want to beat the kids. Yes?
Maybe you can be more sure that you have every possible permutation for the 3 points.
Okay, so good. So one possibility is there may be a coding error. And this is related to the point I was going to say. So later in the semester, we'll talk about Thomas Hale's proof of the Kepler conjecture on the optimal way to pack spheres in 3 dimensions. People have known the answer for years, but he was the one to finally come up with a proof. It involves linear programming to reduce an infinite dimensional problem to a 150 dimensional problem. And you know, one of the big questions in the field is the proof correct? There's 40,000 lines of code. Is the code right? The more complicated your code, the more likely it is that you've made a mistake somewhere. And so I can code using symmetry, but it takes more time to code, and there's a danger that I forgot something. Whereas if I do something like this, it's much faster. Let's get a sense of how big is 24 choose 4. So 24 choose 4 is approximately 24 to the 4 divided by 4 factorial. I'm overestimating a little bit. What's 4 factorial? 24. So this is approximately 24 cubed, call it 30 cubed, call it 27,000. If I have to do this by pen and paper, can I do 27,000 things with pen and paper? I would have accepted either no or yes. Right? I can, I don't want to. 27,000 is too much for me to do with pen and paper. Can a computer do 27,000 cases like this? In a heartbeat. Not a problem for a computer. So when you're doing coding, when you're trying to figure out how to solve the problem, if the cost of creating the optimal code is much longer than running the code, it's not worth doing it. And this is a really important principle in programming. Now, if you're going to be doing something many, many times, you might care about that savings. If this is a calculation we're only doing once, we don't really need to worry about the savings. Do something that's easier to code. Okay? So for this, I would just do the simpler coding. And in fact, even 25 choose 5, that's no problem. It's a small enough number that the computer can do it without any difficulty. All right. So what I want to do now is I want to go back to this problem, and I want to revisit it. So we've talked about one way to solve the problem, just 25 choose 5. We talked about another way, use symmetry a little bit. There's a way to use duality. So what duality is the following. I don't want to solve your problem, I want to solve a related problem, and then if I can do my problem, I can do your problem. So I want to find a problem that's equivalent to looking how to place 5 queens on a board such that 3 pawns are safe. What's an easier problem that is equivalent to this? So it's 3 queens and 5 pawns, and so I will place 3 queens so that 5 pawns are safe. And after I do that, then I do the exchange operation. I change queens to pawns and pawns to queens. Any physics majors here, or people taking physics classes? All right, so I apologize, that's could be a little confusing if you take physics. Okay? Why is this a better way of looking at the problem? How many ways do I have to place 3 queens on the board? 25 choose 3. 25 choose 3 is smaller than 25 choose 5. And if I use symmetry, it's even better. It's then 6 times 24 choose 2. So there's a huge savings here in looking at the dual problem. This is worth really driving home and thinking about. Yes?
So how does that work, though? How would that just switch between the...
Well, so if I can find a way to place 3 queens so that 5 pawns are safe, I did write it down so I get things in the right spot. Okay, so and I think I want to do it queen, 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 pawn, 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 pawn. All right, so if I do it like this, the queens kill this column, they kill this column, they kill this column, they kill this column and row. Sorry, some of these are rows. They kill this, they kill this, they kill this, they kill this. And the 5 pawns are safe. So if I look at this configuration, I have placed 5 pawns so the 3 queens are safe. Now I change all the pawns to queens and all the queens to pawns. And when I do that, queen, 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 and this becomes a pawn, pawn, pawn. Well, if this queen could kill that pawn, then if I just flip their roles, then when that was a queen, it would have killed this pawn. So if I can solve this problem, I can solve the other. And I have converted my problem to one that's a significantly faster computation. Now again, this problem is a cookbook problem. It's a problem we really don't care about, but it illustrates the point that you can rearrange the computation, and you can often have a simpler computation, and that has enormous savings. So frequently, rather than studying the original problem you want to do, you often study a dual problem. How many of you have taken differential equations? So sometimes you might see things like the Fourier transform or the Laplace transform, where you convert a differential equation to another one and solve it there. Sometimes it's easier to move to another space, solve the problem there, and move back. This is spiritually similar. It's where do I want to solve the problem? Okay? So any questions about this idea of duality? Okay. Everybody's on board, everybody's comfortable with this? You all agree, good thing? And somebody will sit next to me at colloquium and have the tic-tac-toe problem ready? All right. So what does this have to do with linear programming? So we have the canonical linear programming problem, and we have the dual problem. So can someone tell me the conditions in the canonical, in the canonical linear programming problem? I have 3 things. What are the 3 things I have? Yes? Ax equals b, and b is b1 through bm. All right, what else do I have? Constraint on the x's, and so the x's are greater than or equal to 0, and it's x1 through xn. And what's the last one?
Some function you want to maximize.
Right, which is it?
Maximize.
Which is it? It's, yes, correct, it's minimize. So I want to minimize C transpose X. And this is the canonical linear programming problem. I can put everything into this form. Is it always a good idea to put things into this form? Not necessarily, right? But I can do this if I want. Okay, so now let's look at the dual problem. So the dual problem is Y transpose A, and I wanted to make sure I do this correctly, is, I think, less than or equal to C transpose. I have Y has how many components? So it has m components. So Y will have m components. Come on, camera, there you go. Y has m components. And we're going to assume they're all real. And then the last one is I want to maximize Y transpose B. Okay, so it's very similar to the original problem. There's a nice exercise which I'll leave for you to do, I think maybe as homework, to prove like the dual of the dual is the original problem. So these are related. Is it clear that they're related? Yeah, I mean, if you look, I've got A again, I have C again, I have B again. I don't have X, but I have a Y. And if A, if I look at it as a matrix, it has to, if it's if x has n components, it's got to have n rows, and then since B has m entries, it's got to have, it's got to have m rows, n columns, so I can do the matrix multiplication. This then tells me the dimensions that y has to be, if I'm going to have y transpose acting on A. All right, so it's not immediately clear why we want to look at the dual problem, but it's clear at least that this is related. And so it turns out that if you know information about solutions to the dual problem, you know things about solutions to the original problem. And that's why this is so important in the applications. And so what we're going to do is the following. This is the key lemma. And this is the reason why we care about dual problems. Lemma. Say x hat is a feasible solution for the canonical linear programming problem. Say y hat is a feasible solution for the dual problem. So feasible means exactly what you would expect. It's feasible means it satisfies the constraints, but I say nothing about the function I'm trying to maximize or minimize. So on the diet, it's a diet that will keep me alive. It may be over budget, but it will keep me alive. If I'm running a movie theater, it is a valid way of choosing which movies to show on screens. I may go bankrupt, but it's a valid way. Okay? So imagine you have a feasible solution for the canonical linear programming problem, and imagine you have a feasible solution for the dual problem. Then we have the following relation. I just want to make sure I get it right. Okay. Then y hat transpose B is less than or equal to C transpose x hat. Okay. And if equal, then x hat is optimal. Right? So this is worth staring at for a minute or two. Solutions to the dual problem give me lower bounds for solutions for the function I'm trying to minimize for the original problem. Because of this inequality, if y hat is any solution of the feasible problem, I cannot have a solution of the original problem where C transpose x hat is smaller than this. So if I'm trying to minimize, I can't get lower than this amount. So imagine these two are not equal. Imagine this equals 100 and this equals 200. What do you know about the optimal solution if this is 100 and this is 200? So what do we know about the optimal solution to the original problem, if it exists, if this is 100 and that's 200? Yeah. So when we're trying to minimize, it's C transpose x. It's C1x1 plus C2x2 plus C3x3. For the diet problem, when we were trying to figure out, that would be our cost. So we had x1 units of steak maybe, and x2 units of cereal, and it was, I think, $2 per unit of steak. Oh, maybe was steak the second one? Okay. I think steak was the second one, and cereal was the first one, and that would be my total cost. I'm trying to minimize the cost of my diet. And so C is just the fixed thing that we use to get a function that we're trying to minimize. So if this equals 100 and this equals 200, what can you tell me about the optimal solution? Yes?
You can't really say anything, can you? Because the way you wrote it, the if only works in one direction. So we know that y times b is less than or equal to, but we don't know that means that there is a smaller x.
Correct. But we know. But if an optimal solution exists, what do we know about it? Between 1 and 200. So this is how answers on the dual give us bounds to answers on the original. So imagine you have some feasible solution to the original problem, and you have some feasible solution to the dual. Then the true optimal, if it exists, and it may not exist, but the true optimal, if it exists, has to be between these two numbers. So you have a way of quantifying how close you are to the optimal solution. It could be an overestimate. Maybe the optimal solution is 150, and you say, I'm 200, I'm within 100. Yes, you're within 100, you're also within 50. So we may not get the best answer for how much we're off by. What would it mean to have the best answer to how far off you are? You know what the answer is, right? If I know I'm off by exactly $53, all right, I now know what the optimal value is. It's 53 less than what I have. You should not expect to be able to prove exactly how far off you are. Anytime you're estimating an error, you've got to expect you're going to overestimate. So that's why this is so important. Okay? So the question is, how would we prove something like this? So the proof is simple linear algebra, but it's a question of what do we want to look at. So when we have this, I'm trying to think what's the best way. I'll go to this board because I want to have all this stuff being shown. So let's look at all the different things that we have. So if we walk, come on camera. All right. So if we walk and look at the other board, all right. I think it's falling out. Yeah. Oh well. The old-fashioned way. All right. So if we walk like this now to this board, and we look at all the different stuff we have, let's see what's going on. We have an AX equals B. We have a Y transpose A is less than or equal to C. We're seeing X and Y both involved with A. I want to find some expression that uses both X and Y, and that I can then start to analyze two different ways. So what I'm hoping this suggests is to study I'll put in my hats, because I'm looking at my feasible solutions. I claim that this is a really good thing to study. Why is this a good thing to study? If I look at it as A times X hat, I can analyze this by using things about the canonical linear programming problem. If I look at it as Y hat transpose times A, I can look at it as things coming from the dual. And so I want to just view this two different ways. This is a really good expression to look at. You may have seen something similar to this when you were looking at eigenvalues in linear algebra. I know it's dangerous to assume memory of things from linear algebra. So if people want, when I'm done with this, I will go through and prove some things about eigenvalues in linear algebra. It might not be a bad idea to just review some of those stuff. As to, this is a good expression to look at. It takes what I want to know from both of them, and it combines them in such a way. All right, so let's see if we can now, okay, so just like walking this way. So now we have Y hat transpose AX is Y hat transpose AX. It's all about grouping. What do we know about Y hat transpose A? It's at most C transpose. So this part over here is greater than or equal to C transpose X hat. Okay. What do we know about AX? What does AX equal? B. So this is Y hat transpose B. Well, Y hat transpose B equals this, which is greater. I think I must have something reversed. Oh, sorry, thank you. I have this reversed. Thank you. Y hat transpose A is less than or equal to C transpose. All right, so Y transpose B is equal to this, which is equal to this, which is less than this. So this is greater than or equal to that. And there's our lower bound. So we just follow the inequalities. And so that proves this part. And now the remainder is that if they're equal, then X hat is optimal. All right, well, we know that no matter what solution you have, Y hat was any feasible solution. X hat was any feasible solution. So imagine we have equality. So now, assume equality. All right, so what would it mean to have equality? Well, whenever I had a less than or a greater than, I have to replace it with an equal sign. Imagine this is not optimal. What would it mean if this is not optimal? So what does it mean if this is not optimal? There exists one that's smaller. So if it's not optimal, we can find an x tilde such that C transpose x tilde is strictly less than C transpose x hat, which equals y hat transpose b. But wait a minute. We just proved that no matter what feasible solution you have for the original problem, it can't be less than a feasible solution to the dual. We've just now found one that's less than the feasible to the dual. Contradiction. And that proves that you cannot have an equality unless x hat is feasible. So we now have a condition to determine when we have hit an optimal solution, right? If we can find a solution to the dual problem such that our solution to the original problem has the same value as this to the dual problem, we've hit the optimal. Are you happy? We now have a test for optimality. This is good. Is this a useful test? If the dual problem is easier, if we can somehow find a solution to the dual problem and a solution to the original problem where this is equal, yes. So unfortunately, it's not clear at all whether or not this is useful yet. It's clear that this is a condition, but it's not clear that this is a useful condition. Right? And that's one of the dangers in something like this, is that just because you have a condition does not mean it's a useful condition. Okay. Any questions on the proofs we've done? All right. So we have 10 minutes left. We have two options. I can start talking about basic feasible solutions and the next round of theory, or I'm happy to review a little bit of linear algebra and fun games of tic-tac-toe. First loud voice wins.
Tic-tac-toe.
Okay. It's linked with linear algebra. You've got to do the linear algebra first. All right. So finding eigenvalues. So we say AV equals lambda V, V naught equals 0. V is the eigenvector. Lambda is the eigenvalue. And we often want to prove things about eigenvalues. So for example, if A is real symmetric, that implies lambda is real. Another one is Q is orthogonal. That means Q transpose Q is Q, Q transpose is the identity. Then the absolute value of lambda equals 1. And this is actually true if we replace orthogonal with unitary as well. So the question is, how do we prove statements like this? And so for example, it's also true, unitary. How many of you have seen unitary matrices? Okay. So a matrix is unitary. It's the complex version of a orthogonal matrix. And so here, it would be UHU equals UH is the identity. So H means the complex conjugate transpose. I take the transpose, and then I take the complex conjugate of the entries. So you've got to be very careful in a lot of the stuff when you're dealing with linear algebra, if you have complex values, that you deal with them correctly. All right, based on the fact that not many of you have seen complex stuff, I will be a little careful on that. All right, so let's do, say, the real symmetric. So we'll do more general. more generally, if AH equals A, we call this matrix Hermitian, then the eigenvalues are real. And here's the proof. Let V be an eigenvector with eigenvalue lambda.
What is AH?
So it means the complex conjugate transpose. I take the transpose and then I replace every number with its complex conjugate. So if I have A plus IB, I go to A minus IB. So I take the transpose, and every time I see an I put in a minus I. So if I look at the quantity V Hermitian V, this is going to be V1 complex conjugate, V2 complex conjugate, Vn complex conjugate, dotted with V1, Vn. And when I take the dot product like this, I'll get the absolute value of V1 squared plus the absolute value of Vn squared. This is the length of my vector V squared. And I just want to give you a little bit of an introduction to complex entries just because this is something that's often glossed over. So for example, let's say I give you the vector 1 comma I. What can you tell me about the length of this vector, where I is the square root of negative 1? What would be true about the length of this? Root 2, non-zero. So if you calculate the length by looking at the vector transpose times the vector, the standard dot product, it would be 1 comma I dotted with 1 I. You'd get 1 squared plus I squared, which is 0. So if you want to take the length of a vector, you have to take not the transpose, but the complex conjugate transpose. Otherwise, if you have a vector that has imaginary components, you're going to get a 0 dot product at times. So you've got to be very careful. So if I look at V Hermitian V, that gives me the length of my vector V. So what I can do now is I can come back and I can calculate the quantity V Hermitian AV. And I'm going to calculate this two different ways. So I have V Hermitian AV equals V AV. What does AV equal? Well, V is an eigenvector, so this is going to just be lambda times V. So I get lambda V Hermitian V. On this side, I've assumed my matrix V is Hermitian. It's equal to its own complex conjugate transpose. So A is the same as AH. So I get V Hermitian A Hermitian times V. Well, the transpose of a product is the product of the transposes in reverse order. It's the same with complex conjugation as well. This is AV Hermitian V equals lambda V Hermitian V. Okay, well, AV is just lambda V. So I have lambda V Hermitian V equals lambda V Hermitian V. I now take the complex conjugate transpose of this. This gives me the complex conjugate of lambda times the conjugate transpose of V. So I get lambda bar V Hermitian V equals lambda V Hermitian V. And now what's important to note, the length of V is non-zero because I assumed I don't have the 0 vector. So I can cancel this from both sides, and I get lambda bar equals lambda. Lambda is real. If you haven't seen complex numbers, we're not going to do too much with them in this course, but this is at least a way to get some of the calculation going. This battery is really having trouble today. This is a way to at least get some of the calculation going. And just see some things, get them on your radar screen before you get to senior seminars. Because if you haven't seen complex numbers, I'll put up a little bit of stuff so that you can review it. You've got to be very careful. You could try to prove all this using just transpose. The problem is, if the eigenvector has imaginary components, V transpose V could be 0. And what you would get is the eigenvalues associated to eigenvectors that only have real entries are real. So there's a couple of subtle issues going on here. Yes?
So the same way that for a given complex number Z,
Mm-hmm.
Z complex conjugate times Z is greater than or equal to 0. So the complex conjugate of a single number.
Right, because this is going to give me a sum of complex conjugate squares.
So the Hermitian is kind of like an analogy when it comes to matrices.
Yes.
Just as you get a greater than or equal to with single complex numbers, the way to think about the Hermitian operator is that it also gives you that sort of notion of length.
It gives you the notion of length, right? Exactly. Yes.
I'm not really sure what you do going from your second to second.
From here to here,
Yes.
I'm assuming A equals AH. So we're looking at a special class of matrices where A equals AH. These are the Hermitian matrices. If everything is real, these are the real symmetric matrices. So it's a special result. All right, so I'm going to now give you a quick version of tic-tac-toe that's fun. Tic-tac-toe plus fun. Right. You start off with the standard board. You have 2 players named 1 and 2, and they each start off with $1,000. And we'll let you bet any real number. Okay? How many of you have seen this? This is bidding tic-tac-toe. You bid for the first move. Whoever bids the highest gets the first move. And there's 2 ways you can play. One way is whoever bids the highest, they give the money to me. Hope the light is still on. Yes. They give the money to me. Or they give the money to the losing bidder. It's more interesting if you give the money to the losing bidder. And then you keep playing. So you keep going until the game ends. And now the question is, what is the strategy? It's not as clear now what the strategy should be. Do you want the first move?
You want it for $1.
So the question is, how much is that first move worth to you? Which moves would you love to have? I'm sorry? All the moves. Not going to happen. You'd love to have 3 consecutive moves. So you're quite willing to lose the bidding for the first 2 if you can then win moves 3, 4, and 5. So the question becomes, how do you play something like this? What is the optimal strategy for something like this? So if you want, this is a fun game. I'm happy to play people with this. The other version is Gobble Tic-Tac-Toe, and I can bring this to class, or Russian doll tic-tac-toe. How many of you have seen the Russian dolls where you have the big doll, and it swallows up the little doll, which swallows up the little one, which swallows up the Ukraine, which swallows up, oh, sorry. All right, so you have the Russian dolls like this, okay? And so the way this is played is you have 2 big, 2 medium, and 2 small. And on your turn, you can place down a doll on an empty square, or you can swallow. And you may swallow one of your own pieces. And I was playing, the first time I taught operations research, I was playing with the student, and the only way they were able to stop me from beating them was they actually swallowed one of their own pieces. And we had to look up in the rules to see if that was allowed. I've only lost to 1 student at Williams, and that actually went in his letter of recommendation and helped him get a job. Is he figured out how to play with me, and he was able to adapt in real time. So if people want, I'm happy to bring Gobble Tic-Tac-Toe. What is the optimal strategy and how to play something like this? So to me, these are 2 variants of tic-tac-toe that are fun. Okay, so what we will do for the next class is we will go and we will start dealing with feasible solutions. So here you're going to need to know a little bit about linear algebra, maybe a little bit about projections, about finding solutions, counting solutions. Okay.